Picture this. A towering rocket stands ready on the launch pad, fueled up and raring to go. The countdown echoes, 10, 9, 8, ignition. With a blinding flash and a deafening roar, hot gas erupts from the bottom of the rocket. This powerful force, called thrust, propels the rocket skyward. As the rocket ascends, it battles against the invisible force of gravity trying to pull it back down. But the rocket's engines are relentless, burning fuel and generating immense thrust to overcome Earth's gravitational grip. Higher and higher it climbs, a fiery arrow aimed at the stars. Rockets don't have wings like airplanes. So how do they fly? It's all about action and reaction. Imagine you're floating in space. If you throw a ball in one direction, you'll start moving in the opposite direction. That's Newton's third law of motion. For every action, there is an equal and opposite reaction. Rockets work the same way. They burn fuel inside their engines, creating hot gas that blasts out the bottom. This is the action. The reaction is the rocket being pushed upwards. The faster and heavier the gas shoots out, the faster the rocket goes. Earth's gravity is a powerful force. It keeps your feet on the ground and makes what goes up come down. To escape Earth's pull and reach space, rockets need tremendous power. They must reach a certain speed and altitude to break free. We call the boundary between Earth's atmosphere and outer space the Kármán line. It's about 62 miles or 100 kilometers above sea level. But simply reaching the Kármán line isn't enough to stay in space. Imagine throwing a ball horizontally. The harder you throw it, the farther it travels before hitting the ground, right? Now, imagine throwing it so fast that, as it falls, it keeps missing the Earth because of Earth's curvature. That's the idea behind staying in orbit. To stay in space, rockets need to achieve a specific speed called orbital velocity. This velocity depends on the altitude of the orbit. For low Earth orbit, where many satellites reside, the speed is a blistering 17,500 miles per hour, or about 28,000 kilometers per hour. Reaching those incredible speeds requires a lot of fuel. That's why rockets are built in stages. Think of it like a multi-story building, with each floor having its own engine and fuel tank. The first stage, the biggest and most powerful, blasts the rocket off the launch pad and through the thickest part of the atmosphere. Once its fuel is spent, this stage detaches and falls back to Earth. The second stage, now carrying a much lighter load, ignites and continues pushing the rocket to its final destination. Astronauts in orbit appear to float effortlessly. We often call this zero gravity, but that's not entirely accurate. It's actually a state called microgravity. While gravity is still present in space, it's much weaker than on Earth. Imagine you're on a roller coaster plummeting down a steep drop. You feel weightless for a moment, right? That's similar to what astronauts experience. They're essentially in a constant state of free fall around Earth. Because they're falling at the same rate as their spacecraft, they appear to float inside. Microgravity has some fascinating effects on the human body. Without gravity pulling on their bones and muscles, astronauts can experience bone loss and muscle weakening. Their fluids also shift upward, which can affect their vision. Scientists study these effects to learn how to keep astronauts healthy during long space missions. By understanding thrust, velocity, and microgravity, we've unlocked the secrets to space exploration. From launching powerful rockets to orbiting Earth and beyond, these concepts are the keys to our journey into the vast universe.